Welcome to The Explainer. Today, we're going to follow the incredible journey of a single carbon dioxide molecule. We'll see how it goes from being, a major climate problem to becoming a valuable new material. It's a pretty wild ride from capture to a whole new life. All right, so here's the game plan. First, we'll tackle why we even need to capture carbon. Then, we'll get into the nitty-gritty of how we do it, how we move it around, and then the really cool part, what we can actually do with it. It's a whole life cycle, so let's jump in.
Okay, first things first, why are we even talking about capturing CO2? I mean, what's the big deal? Well, it all goes back to this really fundamental process that keeps our planet livable, but it's a super delicate balance.
Right, so you've probably heard of the greenhouse effect. Think of it like a natural blanket of gases that keeps Earth from freezing over. It's a good thing. But the problem is, when we pump way too much carbon dioxide into the atmosphere, that blanket gets thicker and thicker. And just like a heavy blanket on a summer night, it starts trapping way too much heat, and that's what causes the planet to warm up. And that's exactly where these carbon capture technologies step in. The whole point is to basically grab that CO2 before it even has a chance to make that blanket thicker. It's a powerful tool in our toolbox for trying to slow down global warming.
So that brings us to the next big question. How in the world do we actually catch these tiny CO2 molecules? I mean, think about it. How do you pick out one specific gas from a huge cloud of other stuff coming out of a power plant?
Well, the most common way is something called post-combustion capture, and it's basically a four-step dance. So first up, you take the hot flue gas from a power plant, cool it down, and push it into a big column. Okay, step two. Inside that column, there's a liquid called an amine solvent. The best way to think of this is like a chemical sponge that is super, super picky. It only wants to soak up the CO2 molecules. Then, for step three, you take that solvent, now full of CO2, and move it to a different column. You heat it up, and that heat forces the solvent to let go of the CO2, releasing it as a pure stream. And the really clever part is step four. The now empty solvent gets sent right back to the start to grab more CO2. It's just this continuous, slick loop.
But that's just what we're doing now. What's really exciting is what's on the horizon. Scientists are working on these advanced hybrid systems that mix and match the best parts of different methods. And the whole point, of course, is to make this process way more efficient and, cheaper.
All right, so we've done it. We've snatched the CO2 out of the air. We've got this pure stream of it. But it can't just hang out at the power plant, right? It's got to go somewhere. This is where its big journey begins.
Which, of course, brings up the next obvious question. Now that we've caught it, what do we do with it? How do we get it from point A to point B? And let me tell you, the logistics of moving all this captured carbon is a huge, huge piece of the puzzle.
Well, there are a few ways it travels. We're talking about a massive operation here. For shorter hauls, you might see specialized trucks on the road. For going overseas, it's loaded onto ships. But for the really big, continuous volumes, the workhorse of carbon transport is a dedicated network of pipelines. Okay, so our little CO2 molecule has finally arrived, and now it comes to a major fork in the road. It has to choose one of two very different paths, two completely different fates.
So choice number one is storage, what's officially called sequestration. This is where we basically lock the CO2 away deep underground, hopefully for good. Choice number two is transformation, where we actually turn it into something new and valuable. Let's dig into that first option, storage.
Yeah, so the most common way to do this is what's called geological storage. We're literally injecting the CO2 way, way down into the earth. The ideal spot for this is in what are called deep saline aquifers. Just think of these as giant spongy rock layers, deep underground, that are already filled with super salty water. They're perfect natural containers that can trap the CO2 and keep it locked up for thousands of years. But you can't just pump it in anywhere. The conditions have to be just right. You need to go deep enough where the pressure is immense. At that pressure, something really weird happens to the CO2. It becomes a supercritical fluid. It's not quite a liquid, not quite a gas. It's this dense, flowy state in between, which is perfect for packing it in tightly and making sure it stays put for a very, very long time. Okay, so that's storage. But now, let's talk about that second path. And honestly, this is the really mind-blowing part. This is where our CO2 molecule gets a second act. What if, instead of just burying our problem, we could actually turn it into a solution, into something valuable?
One of the coolest examples of this is a process called methanation. It's a fantastic illustration of this idea of turning a waste product into something useful. We're talking about taking CO2 and turning it into a valuable energy source.
The chemistry behind it is actually pretty neat. You just take your carbon dioxide, you add some hydrogen to the mix, and boom! A chemical reaction happens, and out comes methane, which is the main ingredient in natural gas, and you get a little bit of plain old water as a byproduct.
And methane is just the beginning. I mean, look at this list. Captured CO2 can become a building block for so many things. You can react it to form carbonate minerals. We're literally talking about turning air pollution into building materials like concrete. How amazing is that? Or it can become key industrial chemicals like formic acid or stuff used to make plastics and solvents. Now, a lot of this is still in the early stages, but the big picture idea is to create a truly circular carbon economy, where the CO2 we used to think of as waste becomes a valuable resource we can use over and over again. Okay, but there's a catch. These incredible transformations, they don't just happen magically. On their own, these reactions can be super slow, or they might need a ton of energy to get going. They need a little push, a helping hand, from some very special materials. And those helpers are called catalysts. They are the true unsung heroes of this whole story. The best way to think about them is as chemical matchmakers. They grab the CO2 and other molecules, bring them together, and help the reaction happen way faster, without getting used up themselves. And there's a whole toolkit of them. You've got things called metal organic frameworks, or MOFs, that are like tiny little cages for molecules. You've got titanium dioxide, which can actually use sunlight to power these reactions. You can even use metal electrodes like gold to get the job done. Each one is a specialized tool to make this whole transformation process faster, better, and more efficient. So when you put it all together, the potential here is just massive. We're looking at a future where we can take a major climate problem and turn it into fuel, into chemicals, into the very materials we use to build our world. It really makes you wonder, doesn't it? Could the pollution from yesterday actually become the foundation for tomorrow? It's a shift from just managing waste to seeing it as a genuinely valuable resource. Thanks for following this journey with us on The Explainer.